are you guys doing this Wednesday? Just about ready to get started here. How was the homework? Is it all right? What's up, Chris? How are you doing today? I'm doing pretty well myself. It's a scorcher out there. I wasn't outside for too long, but for the amount of time I was outside, holy cow. I went to the chiropractor this morning, got an adjustment. I don't know if any of you have ever been to the chiropractor. It's a pretty sweet experience. Get your spine back in alignment. Help with lower back pain, neck pain. If you sit in a chair all day, I try to stand up more. Like when I'm doing these streams, I stand up. But supposedly that's helpful. All right. Let's get to it, guys. No more delay. Today we are going to talk all about particular solutions. Let's get right into it. So last class we learned about how to deal with higher order systems. So the good news is higher order systems are just combinations of first and second order systems. So if you know how to deal with those, then you can basically deal with any nth order system where n could be 10, 20, 30, and so on. So I'm going to give an nth order differential equation just like a general form. So dn dt to the n. So we have like an nth order derivative. And this equation is just supposed to represent a catch-all for a linear nth order equation we might encounter. So these terms go all the way down to like a first order term, and then a zero order term, And we're going to set this equal to a forcing function, f of t. And we're going to introduce a couple different typical forcing functions today. And all of those result in different kinds of particular solutions. Now, a differential equation is not complete without initial conditions. And there has to be at least n initial conditions. So let's just make up a couple here. I don't know, typically you would have something like this. Like the n minus 1th derivative at time equals 0 equals something all the way down to the first derivative at time equals 0 will equal something all the way down to the 0th order derivative itself would equal something. All right, so this is just generic nth order differential equation, linear, with some forcing function and then n initial conditions. All right. Now, if you solve this, the complete solution would be x of t is a homogeneous part, which we're now pros at getting the homogeneous. And then you have the particular as well. The homogeneous part, let's say this is nth order. So we'd have n roots. Pros? Yes. You're a professional now, Phil. Certified in getting homogeneous solutions. I bet I could give you any nth order differential equation and you could give me a homogeneous solution. Hopelessly optimistic. Hey, there's worse things to be. So we would have n roots, let's say like a1 e to the lambda 1t, a2 e to the lambda 2t, all the way up to the nth root. Now remember, some of these roots could be complex. So if you have a complex exponential, like say lambda 2 is a complex root, we know that we can write those as sine and cosine terms. But all of those originally come from an exponential. All right, let's give the general form of the particular solution. So here is the beginning of our new content. All right. The particular solution is going to be a summation of the forcing function itself multiplied by some coefficients and you're also going to have the derivatives of this forcing function. And we'll do a bunch of examples today to illustrate this. But the general form of the particular solution goes all the way up to the nth derivative of your forcing function. So n is the order of the original differential equation. And that's how many derivatives you would have to take of your forcing function. Okay. Let's go right into some examples. Whoa. What are these hyperbolic sines and cosines and tangents doing in my chat, Chris? Nobody wants to see that. Okay. Let's do our very first example of the day. So let's look at this differential equation. This is a first order differential equation. Let's zoom in more. So first order, you can tell because there's just one derivative of the dependent variable. Just testing your I said linear equation, Chris. Okay, so n equals 1 if we're relating up to the above. So we're starting kind of simple. And f of t equals t squared. Chris says, haha, my bad. We're just doing linear differential equations in this class. All right, so what is the particular solution in this case? Well, let's use the this general form up above as a template. So it's going to be C1 f of t, and then we go all the way down to the nth derivative. Well, fortunately, in this case, there's only one derivative. Oh, you know what, though? I think I have to put an n plus 1 here. Yeah, up here. Yeah, that'll go to an n plus 1 term. Okay. So we're going to go, we have to add another term, C2, and then d dt of f of t. And let's plug in f of t. So C1 times t squared plus C2 times the time derivative of t squared, which is just 2 times t. So let's say it's 2 C2 times t. But you know what we tend to do? So we want to solve for what these coefficients are. But it's easier, since this is just 2 times C2, it's easier to just replace this with some coefficient, because these are just constants anyway. So I'm going to make up a different coefficient for that one. I'll just call it D2. So So I'm just putting one number out in front. All right. Our next step is to solve for these coefficients. So what is C1 and what is D2? Well, you solve for these by plugging your general form of the particular solution into the differential equation. So let's do that. So we have our particular solution is C1 plus C1 times T squared plus D2 times T. And when we plug this into the differential equation for X, we're also going to need the first derivative. So why don't we get the first derivative of this? It would be 2C1 times T plus D2. Okay. So I'm going to sub this in. We're going to have 2C1T plus D2. So I'm substituting this into the differential equation up above. Plus 10 times xt, which is just C1T squared plus D2T. That's equal to T squared. So we substituted that form of the particular solution into this equation up here. I should have budgeted a little more space for this. That's okay. So now what we do is we let's rearrange this a little bit first. So, okay, we substituted in. Let's rearrange our terms a little bit. I'm going to gather them in terms of like T squared, T. Is the D2 just to clean up the C's? That's exactly right. That's all. That's the only purpose for that. Okay. So I'm going to get my T squared terms. I'm going to get my T terms. And then I'm going to get any other terms. Okay, T squared, T, and then we're just left with D2. And that's all equal to T squared. I'm just double checking my work here. Let's do C1, 10D2. Okay. And now we equate like terms. On the left and right hand side. So what I mean is we'll look at the T squared terms. We'll look at the T terms. I'm going to give myself a little bit more space by squeezing this up a little bit. I'm going to take this, move it up a little bit. Move this up a little bit. Okay. So we'll have the T squared terms. We'll have the T to the 1 terms, which is just T. and we'll have the t to the 0 terms. So you'll see what I'm doing here. So t squared, on the left-hand side, we have 10c1. Now we know the left-hand side has to be equal to the right. On the right-hand side, there's just a 1 in front of the t squared. And I can even explicitly put that in. 1 times t squared. And why don't we expand this out? On the right-hand side, we could have 0 times t plus 0 times t to the 0. So, okay, let's do the t to the 1 terms. On the left-hand side, I have 2c1 plus 10d2. But on the right-hand side, I don't have any t terms. I have 0 times t. And finally, wait, did I mess up here? C1 t squared plus C2. I feel like this isn't going to give me what I want. Plus tens plus d2t. Ten c1 t squared plus 2c1 plus 10d2. Huh. Well, let's keep going with this and let's see what happens. So it looks like I have d2 on the left-hand side, and that's going to be equal to 0 on the right. But that would mean that d2 equals 0, and then that would also imply that c1 equals 0. But that can't be. I must have made a mistake in here. Okay, my particular solution is f of t plus c2 . 2c2t. So I have a t squared term, I have a t term. I took the derivative. Rip, no particular solution, but I know it can't be 0. Do you guys see a mistake in there? Okay, I'll just... If I don't see it in another minute, we'll go to example 2. And then we'll come back to this and try to figure it out together. What's the third second derivative of t squared? Wait, what? What are you saying, Chris? Are you saying what's the second derivative of t squared? What's the third derivative of t squared? Well, I mean, if you have t squared, if you take the derivative, you get 2t. If you take the derivative again, you get 2. And then if you were to take the derivative of that, you get 0, right? So I have c1 t squared plus d2 times t. I took the derivative, 2c1t plus d2. Yeah. I plugged it in. Plus 2c1 plus 10d2. Okay, let's move on. Shouldn't it be 20 with the product rule? What be 20? Are we talking about up here? When you rearrange, what is the 0 times t and 0 times t0? Did you mess up your rearranging terms? Okay. Let's explicitly write this out. So I have 10 c1 t squared plus 10 d2 times t plus 2c1 times t plus d2. But that would mean d2 is 0. And that would mean c1 is 0. Interesting. Right side of equals on rearranged terms. You don't follow? Well, this one, all I'm doing is I'm taking this equation and then I'm just rewriting it. And because I want to equate like terms, like I want to equate t squared with t squared. I want to equate t with t. And I want to do t to the 0. Oh, I shouldn't put a 0 here. Because this doesn't have a t, that's the same as t to the 0. All right, we're gonna come back. We're not gonna be defeated. Okay, let's try this one. So this is a second order differential equation. And we have this linear forcing function on the right hand side. So it's just t. So as time goes on, this will linearly go up as a function of time, and it has a slope of 5. The loop is real? I know, Chris. Stuck in an infinite loop. Okay. So it's second order, so n equals 2, and f of t is 5t. So our particular solution is going to be some coefficient times f of t. And remember, we're going to go up to the nth derivative here. Plus c2 df of t dt. And then we need one more term. d squared f of t dt squared. So let's plug in f of t here. So it would be 5c1 times t plus 5c2. And then the second derivative of 5t is just equal to 0. So it's plus 0. And just to make things a little cleaner like before, I'm just going to rename this d1 times t plus d2. And let's solve for d1 and d2. We're going to do the same thing as last time. And it's going to work. My optimism is going to win out. Okay. So how do we solve for this? We sub it into the differential equation. So we're going to need to solve in f of t. We're also going to have to do the first derivative, which would just be d1. And the second derivative is just 0. So let's sub into our differential equation. So we're going to have 0 plus 1 times d1 plus 10 times d1t plus d2 equals 5t. And let's do plus 0 times t to the 0. Because I'm running out of room, we're going to go over to the side here. Okay, we're going to equate like terms. So let's do just t, or, you know, that's the same as t to the 1. On the left-hand side, I have 10 d1 times t. And then on the right-hand side, I have 5 times t. And then for t to the 0, I'm going to have 1 times d1 plus 10 times d2 equals 0. All right, so from this one, we're going to have d1 equals 1/2. And from this one, we're going to have 10d2 equals negative d1. So d2 equals 1/10 times minus d1. Can't write d1. Okay. So that's going to be minus 1/20. I'm going to move this up a little bit. Oh. And let's fix this over here. I wrote f of t is equal to all this stuff. That's definitely not what it is. This should be the particular solution, xp of t. I'm sorry about that. I think I'm losing my mind today. So where I wrote f of t over here, that should have been our particular solution. All right. So our particular solution is 1/2 t minus 1/20. Now this isn't the complete solution. We're not even worrying about the homogeneous stuff yet. We're just solving for the particular solutions. Let's do another one. Let's scoot this up a little bit. Okay. Hey guys, 1 of 2 was correct. That's 50% success rate. Let's go for 2 out of 3. All right, so we have a first order system again, but this time we're having a sinusoidal forcing function. So we want to get the particular solution in this case. So n equals 1, and f of t is 5 sine 2 pi of t. Okay. So the particular solution is going to be some coefficient times f of t plus another coefficient times the first time derivative. So let's fill that in. So this is going to be 5c1 sine 2 pi of t. Let's put the time derivative over here. 10 pi cosine 2 pi of t. So we're going to have plus 10 pi c2 cosine 2 pi of t. And let's simplify these terms again. So I'll collapse 5c1 to just d1. And 10 pi c2, I'm going to collapse to d2. Just make our lives easier. All right. And then that, because we're going to have to substitute in a first derivative, let's just calculate that. So that'll be 2 pi d1 cosine 2 pi t minus 2 pi d2 sine 2 pi t. Okay, we're ready to sub in to the differential equation. So as we're doing this, this is just showing that the particular solution, you can solve for it independently of the homogeneous solution, and you don't need to use the initial conditions to solve for the coefficients of the particular solution. So that's a difference between the particular and the homogeneous. Okay, so let's sub this in. So I have 2 pi d1 cosine 2 pi of t minus 2 pi d2 sine 2 pi of t plus 10 times d1 sine 2 pi of t plus d2 cosine 2 pi of t. And that's equal to the right hand side 5 sine 2 pi of t. All right, I'll carve out some space. We're going to equate like terms. So let's get all the sine terms together. I'll get all the sine terms from the left-hand side. So I see minus 2 pi d2 times sine. And then I see plus 10 d1 times sine from the left-hand side. And then from the right-hand side, we have 5 sine 2 pi of t. Let's do the cosine terms. So from the left-hand side, we're going to have 2 pi d1 cosine 2 pi t plus 10 d2. And on the right-hand side, oh wait, I shouldn't have that sign up above. Because on the right-hand side, I have 0 times cosine 2 pi t. All right, so we got to solve for d1 and d2. And we could do this by hand, but why don't we take advantage of learning or practicing more MATLAB? So what I'm going to do is I'm going to transform this into a matrix equation where we can solve for d1 and d2. So the first equation will be on top, the second equation on the bottom. So the top equation, I have 10 times d1 minus 2 pi times d2 equals 5. And the bottom one, I have 2 pi times d1 plus 10 d2 equals 0. And what I'm going to do to solve for d1 and d2, let's call this matrix, we'll call it like a fancy A. So I'm going to take the inverse of A and multiply it by 5, 0. I'll get MATLAB set up over here. Okay, so this matrix A that I just made up, it's 10 minus 2 times pi, and then you put a semicolon to go to the next row. You have 2 times pi and 10. So my vector of d values, so that'll be d1 on top of d2. It's going to be the inverse of that matrix times 5, 0. So D1 is the top entry of this vector. D2 is the bottom. Okay, so that's 0.3585 and minus 0.2252. And for completeness, why don't we just write out that particular solution? So it'll be 0.3585 sine 2 pi t minus 0.2252 cosine 2 pi t. And we'll put a box around it. Now I want to go back to the first example, but I'm afraid. We know the particular solution can't be 0. Are you guys prepared to confront failure and learn from it? Such is life, I guess. Don't be afraid of failure. Don't be afraid. We all fail in many different ways, and then we learn from it. Okay. I'm going to try something here. What I'm going to try is I'm going to take another derivative of the particular. So, like, remember in the definition I said only take derivatives up to the order of the differential equation? I'm starting to question that definition. So I just want to try this. Okay. C1 f of t plus c. Wait. Okay, so I'm saying, let's try this. C3 d squared dt squared. I'll just erase this over here. F of t. So this would mean plus C2 so we'll have C1 plus times T2 squared plus D2T and heck, we'll have C2 here. The first derivative remains the same. C1t squared, 2t, that's definitely the derivative, C2. Oh, wait. Oh, but if I take another derivative, it's just 2. That's not a coefficient. Oh, but it's C. Okay, it's 2 times C3. All right, and we'll call that D3. C2 is 2. Okay, I see what you're saying. Okay, wouldn't C2 be multiplied by 0, though? C3 times 2. Yeah, no, it'll be multiplied by 2. So we'll have 2 times C3, and I'll call that D3. Okay. What if I just erase this stuff and like start over clean? Do you think that's a good idea? If I erase this stuff down here? Let's just do it. All right. So we're gonna substitute this. Move it. Oh, shoot. Okay. Good idea. Undo. Let's move you to the side, my friend. This has to work. I mean, what the heck? All right. This is attempt number 2. So we're subbing it in. We substitute in the derivative. So 2c1t plus d2 plus 10 times c1 t squared plus d2t plus d3. So this one is xp dot, this one's just xp. That equals t squared. Let's see what this does for us. So all we changed is we took more than in derivatives. Okay. So we're going to come over here. We're going to equate like terms. Okay, we'll start with t squared. And this one will be same as before. We'll have 10c1 equals 1. And then if we equate t to the 1, we'll have 2c1 plus 10d2 equals 0. And then if we have t to the 0, we'll have d2 plus 10d3 equals 0. I think this will work. But you know what? If this works, it means that our definition that we started this lecture with has a problem. But I got that definition from Dr. Mook, who's the guru of gurus. Okay. C1 equals 1/10. I won't use MATLAB for this one. We'll just grind it out. Then from this one, 10d2 equals minus 2c1. So d2 equals minus 1/50th. Because it's minus 1/5 times c1. So it's minus 1/50th. And then d3 equals minus 1/10 d2, which makes it 1/500th. Hmm. So I think the particular solution is, like, if we go back to this general form, like, what did we learn from this? I think, so should we be taking n derivatives or n plus 1 derivatives? Because that will change all of our answers. Maybe it really should be n plus 1. But it won't change to all. Well, I don't think it'll change these example problems because, like, take example 2. So we had 5t. And we had the first term, we had the first derivative, and we took the second derivative, but the second derivative was 0. So even if we took an n plus, like, so n for this example was 2. So n plus 1 would be 3. If I took the third derivative, I would just get another 0. You know what I'm saying? So it wouldn't affect this answer because that term would go to 0 anyways. And I think that for this problem, we could take another derivative, but if we did, we'd get back another sine term. So what I'm saying is, if, like, let's say we went to the n plus 1th derivative, we'd get minus 20 pi squared sine 2 pi t. And that wouldn't affect anything because I would add that in and I would just end up collapsing, like, that extra sine term into d1. So I'd still have a coefficient times a sine plus a coefficient times a cosine. So I think isn't the third derivative of t squared equals 0 as well for the first example? Well, okay, so the first derivative is 2t, the second derivative is 2, and the third derivative, right, would be 0. But this example was different because this derivative that I included was non-zero, so it did affect the answer. Chris says, that's what I meant originally. Oh, I see. Okay, guys. Let's put a little star here. How do I say this? Keep taking derivatives until you get to until the derivative becomes 0. Or, like what happened with the sine and the cosine, is you started to get back the same functions. So, for example, sine, cosine. So now what I'm going to do, just for the sake of the notes later, I'm going to delete. And I'm going to write, for example, for this one, what did we actually get? One-tenth t squared minus 1/50th t plus 1/500th. Goodness gracious. Good gravy, man. Okay. Let's keep going. So there's two important properties that I want to show you, and they both have to do with linearity. The first property or principle is the scaling principle. C3 times 2 should be correct. So, to talk about this scaling principle, what if, in the previous example, so example 3, what if we doubled the amplitude of the forcing function? So here we had 5 times sine 2t. What if we made it 10? So let's solve for the particular solution in this case. So I already know that it'll be some coefficient d1 times sine 2 pi t plus some coefficient d2 times cosine 2 pi t. Like if I went through the previous steps, I would get to the same point. And I also know that I'd have this. Same thing. 2 pi d1 cosine 2 pi t minus 2 pi d2 cosine 2 pi t. And if I substitute that into the differential equation, well, the differential equation is the same. It's x dot plus 10x. So I'd get the same thing. You don't have to rewrite this. I'm just gonna copy it though. So the only difference is gonna be in the right hand side, where instead of it being equal to 5 times sine 2 pi t, it's gonna be equal to 10. So when we solve for d1 and d2, like we'll get that same matrix as before. 2 pi 10. And the only difference is going to be we're going to have 10 and 0 instead of 5 and 0. And once again, I'm going to go into MATLAB and just calculate this again. So let's call this D vector 2. And the only thing I'm changing, it saved my A matrix from before. This is our new one. Can you go back to the matrix? Yeah, I will in a second. So, oh, do you mean in MATLAB or on the surface? Shouldn't it be plus 2 pi? This one? Are you talking about this term, Phil? So this is from equating the sine terms. So that's from up here. Well, we did that up there. I mean, so you have minus 2 pi times d2 times sine plus 10 d1. So that's where it comes from. I think it's a minus. It's minus 2 pi. All right, so D1 is 0.717. D2 is minus 0.4505. But, okay, let's try something. I'm going to go back to MATLAB. What if I take this vector and I divide each element by 2? So I have to do this dot division. I've talked to some of you about dot multiplication. So whenever you have this dot in front, it does element-wise division or multiplication. And what that means is it'll take every element and divide it by 2. Oh, whoops. I didn't want to divide that one. I want to divide dvec 2, the one we just got. And if you compare this to our original d vector, you notice they're the same. All right, let's unpack this a little bit. So what happened? The coefficients doubled. So let's show this in a picture here. Let's say, so we had 5 sine 2 pi t, and we applied this to our system, and we calculated 0.3585 sine 2 pi t minus 0.2252 cosine 2 pi t. And then what we did is we said, okay, what if I take 2 times that and I put it through the same system? And what we found was that the particular solution was just multiplying the original particular solution by 2. So I'll leave some room here. So 2 times this. So that would double each of the coefficients out in front. So let's write this out in words. If you multiply your forcing function by a constant, the particular solution is also multiplied by that constant. So it means if you have the particular solution for some system and you're like, oh wait, I want to give it a little more input or a little less input, you don't have to solve for the whole solution again. You can just scale it. And this has real life implications as well, where if you know you're working with a linear dynamic system, if you want to increase your output by like 2, well, you know, I just have to increase my input by 2. It may sound, I don't know if some of you think that's obvious, but I don't think it necessarily is. Like, it's just convenient that it works out this way for linear systems. You double the input, you double the output. This makes linear systems so incredibly useful to work with. Yes. It makes them so much easier. Like let me give you an example. If you're working with a motor and you apply some voltage, it'll spin up to some speed. Let's say you're like, oh, that's too fast. I want to cut that speed in half. Well, give it half the voltage, and then it'll go half as fast. Or if you want to speed it up 2 times, well, you double the voltage. Like, that's just a practical example of this scaling property for linear systems. Okay. How about we take a little 3-minute break, and then we're going to go on to the next linearity principle, which is called the superposition principle. It also helps so much for calibration. All right. So I have the time of 3:19 Eastern. Let's start again at 3:23 Eastern. Get in a little stretch. Get some water. Get some coffee. And then we'll come right back. right, guys. We had a short intermission. Let's get back into it. We're blasting through how to get particular solutions today. Okay. So we talked about the scaling property of linear systems, where if you scale your input function by some factor, your particular solution gets scaled by that same amount. Now we're going to do superposition. Ooh, welcome, UB Math Professor. Whoa, 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 whoa. That's a lot of puppies. Let's talk about superposition. Okay. There you go. Okay. So examples 1 and 3. And example 1 was a nightmare. Let's just say that. They have the same homogeneous part, but they have different forcing functions. So example 1 had t squared. Example 3 had 5 sine 2 pi t. So what's going to happen to our particular solution if we combine the two forcing functions? Like we add them together. Goodness gracious. All right, so let's do it. We may not all survive what's about to happen, but we're going to do it nonetheless. So the order is 1, and our forcing function is t squared plus 5 sine 2 pi t. All right, so our particular solution is going to be some coefficient times f of t plus another coefficient times the first time derivative of f of t, another coefficient times the second time derivative, and I think that's as far as we're going to have to go. So our new guiding principle is you have to go as many derivatives until terms start to become 0, or you start to get back the same functions. So why don't we make sure of this, though? Let's take some derivatives on the side to figure out how far we have to go. So the first derivative, 2t plus 10 pi cosine 2 pi t. And if we take the second derivative, that's going to be 2 minus 20 pi squared. Oh goodness, I keep opening that menu. Sine 2 pi t. And we don't need to go any further than this, because if I take the third time derivative, I'm just going to get a 0 here. And you can see with this sine cosine thing, we're like, by the time we got to the second derivative, we were already starting to get the same function back. So we're going to get C1 t squared plus 5 sine 2 pi t. And I'm going to simplify all of this at the end and introduce some new coefficients like we've been doing along the way. 2t plus 10 pi cosine 2 pi t. And we're going to do one more. Plus c3, 2 minus 20 pi squared sine 2 pi t. Now, if we go across here and take inventory of all the different types of functions that we've introduced, well, we have, I'm just going to call all of these coefficients d, because we're going to start like combining some things. But we're going to have something times t squared. We're going to have something times t. We're going to have something just being a scalar. We're going to have a sine 2 pi. And we're also going to have a cosine 2 pi. Goodness gracious, right? We're gonna plug this in to the original differential equation, so we have to take the time derivative of this. 2d1t plus d2 plus 2 pi d4 cosine 2 pi t minus 2 pi d5 sine 2 pi of t. Once again, I didn't budget the appropriate amount of space. No worries. Okay, so we're going to plug this monster into the original differential equation. Maybe I'll change colors just so it looks a little separate. I think I'll take over this space down here as well. We have unlimited space in the digital workspace, in this digital domain. I know. Okay, so we're plugging in to this equation up here. 2d1t plus d2 plus 2 pi d4 cosine 2 pi t minus 2 pi d5 sine 2 pi t plus 10. I got to go prepare for my exam tonight. Good luck with the lecture. Hey, thanks for stopping in, UB Math Prof. Good luck with your lecture. All right. D1, so we're just plugging in this term, D2T, D3 plus D4 plus D5. And then this is going to be equal to our right-hand side, which is t squared plus 5 sine 2 pi t. Whew! That's a lot of writing. Now, what we have to do to solve for D1, D2, D3, D4, D5, we have to equate similar terms from the left and right hand side. Let's do a new color for that. Okay. So the terms we're going to have t squared, we're going to have t to the 1, we're going to have t to the 0, we're going to have sine terms, and we're going to have cosine. All right, let's do the t squared. So I'm looking through all these terms on the left-hand side, and I'm looking for all the t squared ones. So for this, on the left-hand side, we just have 10d1 times d squared. And on the right-hand side, we have 1 times t squared. Now for t to the 1, on the left-hand side, I have 2d1 times t plus 10d2 times t, and then the right-hand side has 0. For t to the 0, I have this d2 term. What else do I have? And then I have 10d3. And then I have no t to the 0 terms on the right-hand side. For sine, let's look at the left-hand side. I have minus 2 pi d5. And then I have plus 10 d4. And the right-hand side has 5. Cosine, left-hand side has 2 pi d4. And it also has plus 10 d5. And the right-hand side has 0 times all the cosine terms. So goodness gracious, we have 5 equations and 5 unknowns, d1, d2, d3, d4, d5. However, let's scroll up a little bit. What I want to do, look at this set of 2 equations. I'm going to copy this. Okay, hopefully that worked. Let's bring that down here. Paste it. And let's take a peek. Look at this. For the sine 2 pi t from that problem, we had minus 2 pi d2 plus 10 d1 equals 5. So the names of the coefficients are different, but the equation is the same. Same for this cosine equation. I have 2 pi d4 plus 10 d5 equals 0. Well, same thing over here. 2 pi d1 plus 10 d2 equals 0. So I know I could solve for d1 and d2 from these 2 equations. So I'm going to get the same coefficients over here. Also, these t squared, t1, t0, if we go all the way back to our disastrous first example, let's grab these. Same thing, we'll copy this, bring it down. Kind of move it over here. We had 10c1 equals 1, 2c1 plus 10 d2 equals 0, and d2 plus 10 d3 equals 0. Same exact equations, and we got these coefficients. Okay. So, fortunately, we don't have to solve this system of 5 equations, because I know that d1 from before, it's going to be 1/10. D2 is going to be minus 1/50th. D3 is going to be 1/500th. D4, what is that one? I think it's 0.3585. And D5 is minus 0.2252. So let's draw a picture for what happened here. And it's a very useful property. Okay, let's... Wow, I'm sorry. I really mismanaged the space here. We'll come back to this example. Maybe I'll put this way down here. Okay. So this is what happened here. From example 1, we had t squared as our forcing function to a system. And we got out, let's call it like xp1. That was the particular solution for that. For the other example, we had 5 sine 2 pi of t. So a different forcing function, but we put it into the same system. And then we got out a different particular solution, xp2t. Now this is what we just did. What if we take t squared plus 5 sine 2 pi t, and yet again, we put it into that same system? What did we get out? The summation of the two particular solutions. So that's very cool. If you know separately how a system responds to certain inputs, then if you combine those inputs together, you also already know what that combined behavior is going to be. So, if you know how okay, let's see. If you know the particular solution for forcing function A, and also know the particular solution for forcing function B, if you apply forcing function A plus B, the particular solution for that is the sum of the separate particular solutions. So what's kind of cool, you can make like a library of particular solutions. Like this is the particular solution for a sine. a cosine, like a t squared, a t. And then you can just pull these out and combine them for a given system when inputs of any flavor come through. So that's superposition. Okay, the very last thing we're going to do today, we're going to take this same system, and so we already know the particular solution to this system, but what we're going to do is solve for the complete solution. So we're going to combine the homogeneous and the particular parts, and we're going to have this initial condition for the system. And then we're going to plot it in MATLAB. I think we've spent enough time slaving over this system. We should see what its response looks like by plotting it. Okay. So, x of t is going to be the summation of the homogeneous and the particular parts. And we already know the particular solution is 1/10 t squared minus 1/50 t plus 1/500 plus 0.3585 sine 2 pi t minus 0.2252 cosine 2 pi t. All right, now let's get the homogeneous part. We know that it's going to be some coefficient a times e to the lambda t, where lambda is the root of the characteristic equation. What's the characteristic equation? It's lambda plus 10 equals 0. So therefore, lambda equals minus 10. But we don't know what this coefficient a is yet. So how do we get that? We use the initial conditions for the problem. So first, we should write out the complete solution. Oh, is my pen going out? Sorry, I have the luxury of being able to copy and paste this. If you're writing this by hand, not as easy. So we know, so this is our complete solution. Now we use initial conditions on our complete solution to get A. So you don't apply the initial condition just to the homogeneous. You have to do it for the complete solution. So x at time equals 0 is -1. That's just the initial condition I listed up above. So if I plug in time equals 0 into x of t, I'm going to get a plus 0 plus 0 plus 1 over 500 plus 0 minus 0.2252. So I just plugged in t equals 0 into x of t. So that means a is -1 over 500 plus 0.2252. Divided by 500, which is minus 0.7768. Now let's go into MATLAB and plot this. Okay. So first what I want to do is I want to make a time vector to plot this over. So I want to plot up to the settling time of this system. So I'm going to calculate the settling time here. It's going to be, well, let's do it slowly. The time constant is -1 divided by the real part of the root, which is -10. And then our settling time is 4 times our time constant. And then I'm going to make a time vector using the linspace command that goes from 0 to our settling time. And I'll put 500 points in there. That sounds good. Let's do our homogeneous part is going to be a times the exponent of lambda times t, where a is -0.7768. But you know what? We could say, even up here, lambda is -10. Or we could even be a little bit redundant, like put the real part of lambda up here. Same thing. Okay, our particular solution was 0.1 times t squared. And notice I'm doing this dot here. If you don't do that, it'll throw an error for you. Times t. Divided by 500 plus 0. So is lambda always positive for tau? Like the abs of lambda? Well, tau is always going to be a positive number. Lambda should hopefully have a negative real part. Sine 2 times pi times t to do 5-2. I must have made a mistake on the homework. Cosine 2 times pi times t. Okay, and then our complete solution is the summation of the homogeneous and the particular parts. And the reason I wanted to break these up too is I want to show you like all on the same plot. I want to show you the homogeneous part. Let's do that in blue. I want to show you the particular part. Let's do it in red. And the combined one, let's show that in black. And let's make like a bold line width of 4. I'll turn on my grid. I'm going to label my axes. Actually, I'm going to put a legend in here. Homogeneous, particular, and complete. And let's run it. 9 times out of 10, when you run your code for the first time, you get an error. We'll see. Hey, we don't have an error. Interesting. Let's plot this to 2 times the settling time, so we can see this a little bit more. Or maybe even 3 times. Why not? Okay. So the black line is the overall solution. And remember, the initial condition for the overall system is -1. And it's probably too small for you to see, but the black line is starting right at -1. Does the legend correspond with the order of the plotted lines? Yes, it does. Yes, sir. This blue line is the homogeneous. And remember, the homogeneous part of our system is just a first order system. And it's stable. So it's just this decaying exponential that goes to 0. If the homogeneous part of your system is stable, it'll always eventually go to 0. Even if it's oscillating, it'll go to 0. Our particular solution looks like this. It's kind of sinusoidal, but it has this t² thing going on too. Now, what I wanted to show you is that you see that the complete solution, the black line, it converges towards the particular solution. And it does that by the time the system settles. So it looks like around 0.5 seconds, the homogeneous it's totally settled. It's not contributing anymore. So the particular solution is the only thing that's left. So that's why we call the particular solution the steady state solution. For most systems that we work with, the settling time is pretty quick. But if the system continues to like operate with some forcing, it'll just look like the particular solution. And we'll reinforce that more and more. What if I make this run to like 10 times the settling time? Ooh, that's where that t² is coming in. The t² just increases quadratically, but it has like this sign superimposed on it. So at this point, the homogeneous solution is gone. We're just left with that particular. Whew! I bet you guys feel like you've been drinking out of a fire hose today with this huge dump of information. We'll keep doing examples. Your next homework is going to be working through more of these examples. They're going to be similar to the things that I showed in class today. So hopefully you can use the notes from today as a nice template to go through that. But that's it. I'm going to hang around here till 5 p.m. You're welcome to hang out as well. Any questions you have, this time is yours. You can ask me any questions about the content from any point in the course. You can ask me questions about MATLAB. But other than that, I just hope you have a wonderful rest of your Wednesday. I hope you get some rest. I hope you get to talk to a friend or two. Have a good meal. Could you go over part 8 of question 3? Sure. My pleasure. Let me pull it up. Let's see here. How about 6, 7, and 8? Yeah, we can do that. That question sucked. That's a tough question. That's a tough question. Alright, where are you? Okay, let's start. Let's take this. This is tricky because you're working backwards. Let's put this here. I'm going to give myself a little boundary over here so I don't just go all over the place. Okay. Take a peek. So, I think what I would do first, I would try to figure out the period of oscillation to like try to get the natural frequency. So you can compare any two peaks. Like this one might be easier. Like you take this lower peak here, compare it to this peak here. And so that means that the period t, you know, I'm just going to say it's approximately 3 seconds. Okay. This means that the damped natural frequency, I'll do it in hertz first. It has 1 cycle every 3 seconds. So that's 1/3 cycles per second, hertz. That means that if I convert it to radians per second, you multiply that by 2 pi. Hold on a second. Let's do that. Okay. Next, Let's try to put an exponential envelope on this. And I'm not looking for like a perfect... Okay. So you can tell that the final value it's converging to is 1. So what I want to do, I'm going to try to estimate the time constant. So the amount of time it takes to get 63% closer. So it starts at 0. 63% is like 0.63. So I'm going to, okay, you got 2.09. I'll just say tau is approximately 2 seconds. Ooh, this color's not showing up very well. All right. Now, we know that tau is -1 over the real part of the root. For zeta, I found another equation online that used delta, another calculated term based on the graph. Yeah, you can do that. Like one technique's called the logarithmic decrement. But I think even this is enough right here. So we know this is a second order underdamped system. So this is the same. The real part of the root is minus your damping ratio times omega n. So, okay, tau. So I know this is equal to 2. So that means that zeta omega n is approximately equal to 1/2. How do I know it's underdamped? Because the graph has decaying sinusoids. The only type of second order system that produces decaying sinusoids is underdamped. Like overdamped, you have this, right? Just like 2 exponentials. If you have critically damped, you have repeated real roots, so it's like a2t e to the lambda t. If you have undamped, you just have pure sinusoids. Omega nt plus a2. I just don't know how to correlate the pictures. Well, what I'm trying to tell you is there's only a certain number of combinations of responses you can get out of a second order system. I mean, there's only 4 types. And underdamped produces these decaying oscillations. So I know that the roots of a second order underdamped system are minus zeta omega n plus or minus omega d I. So the roots of this system are minus 1/2 plus or minus 2 pi over 3i. And once you have that, you're in the home stretch. So how do you get the differential equation? Well, remember, like we're going backwards. But if I was going in the forwards direction, I would start with a differential equation. I'd get the characteristic equation. I'd get the roots. So I already have the roots. So I want to work backwards to the characteristic equation. So the characteristic equation is a polynomial that is equal to 0 when you plug in these roots. So like, I mean, this is a second order system, but I mean, if you had a first order system, like I know lambda's -3 in this case. So if I plug in -3 in here, it goes to 0. I'm going to do something similar here. Let's see. If I take lambda, couldn't you use Pythagorean identity to find the values like on the graph? What values? I'm trying to get the differential equation right now. Oh yeah. I guess we could take that step by step. So I know omega d already, and then so let's do this. Let's say I have like a root here. Right, the vertical is 2 pi over 3. Let's say my origin is like over here. And then I know this is 1/2. I know omega n is this distance. So omega n is square root of 2 pi over 3 squared plus 1/2 squared. I'm going over to MATLAB real quick. So I'm going to take this squared plus 0.5 squared. So this is 2 times pi divided by 3. So 2.15 for my natural frequency. Oops. 2.15 radians per second. And then I could say, so then I could get the damping ratio. I know that it would be 1 over 2 omega n. So 1 divided by 2 times 2.15 is 0.2322. Something like this. All right. So this is another big part. The roots. Okay, so how do you get the characteristic equation? Once again, if you plug those roots into the characteristic equation, it will evaluate to 0. So the characteristic equation should be this. It should be lambda minus lambda 1 times lambda minus lambda 2 equals 0. So if you plug in for lambda 1, then this whole thing will go to 0. Or if you plug in lambda 2 for lambda, this will go to 0. So I have lambda minus 1/2 plus 2 pi over 3i. Lambda minus 1/2 minus 2 pi over 3i equals 0. So this is how you can do this by hand. You lost me with the characteristic equation? Well, Why are you doing it that way? Which way did you do it? I don't always have the best way. Just to preface. Yeah, I'm curious what you guys did. I know ways to do this in MATLAB, which I'm also that's also fine. Okay, got you, Phil. But as far as getting the characteristic equation by hand, this is the only way I know. Or wait. Wait, you don't have to do that. Oh. Yeah, MJ, you're right. Okay. You're right. Okay. So, what MJ's saying, for an underdamped system, the standard form is good. That's a much faster way than what I was suggesting. Okay. How do we plug that in then? Okay. Zeta equals that answer. Omega n equals 2.15. Omega d is 2 times pi divided by... oh, wait, I don't need that. Okay. 2 times zeta times omega n. And then omega n squared. Okay. So I'm going to have lambda squared plus 0.9985 lambda plus 4.6225 equals 0. That's my characteristic equation. So this means that the homogeneous part of my equation let's just move this aside for now. Get out of my face. Is x double dot plus 0.9985 x dot plus 4.6225 x equals 0. Okay. But we know that I'm providing a step input to this system. And I know I wrote unit step in the prompt, but it's so it's 0. But it's not going to be a unit step. It's going to be some just constant other than 1. Let's see here. Wait, shouldn't it be 1? Oh, no, it won't be 1. Okay, so we know x of t. So let's say I'm going to plot this. I know the homogeneous part is going to be let's just write e to the real part t times a1 cosine omega dt plus a2 sine omega dt plus, let's call it d, some constant. And I know that the initial condition, it starts at 0. So that's going to be a1 plus d equals 0. And x dot 0. Oh, it's always this thing. So the time derivative, I always have to write this out because I forget. This is like such a, that's the annoying part. Okay, so x dot 0 is minus zeta omega n a1 minus omega d a2 equals 0. Let's see. Oh, wait. XP. So why did you not just solve the homogeneous part first and then the particular part? When I was just doing the homogeneous part, my a1 and a2 kept being 0. That shouldn't happen. If you get a1 and a2 to equal 0, that means you have some sign error. Okay, so the particular solution is some d. So if I plug this into the original equation, 4.6225, d equals a. So d equals a over 4.6225. And could you just solve the homogeneous part for me alone? Oh, yeah. Let's assume that a equals... Let's assume that a equals 1, like it was a unit step. Okay, so that'll give us d. So we'll assume that d is known. So a1 is going to be minus d. But MJ, I'm solving the homogeneous part right here. And I'm not getting coefficients to be 0. Oh, I see, MJ. Because you need you need this particular piece. You need it with the particular. Because, yeah, you will get 0 if you solve for these coefficients, A1 and A2. If you assume the initial conditions are 0, you will get 0. Whenever you solve for these coefficients, A1 and A2, it has to be along with the particular solution. Okay, so A2 then will be minus zeta omega n A1 over omega d. Holy cow. Let's do it in MATLAB. So I have to put in all of this stuff. Omega n, omega d, and we'll say A equals 1. That's like my input. I'll say D is A divided by 4.6225. And A1 is minus D. A2 is minus zeta times omega n times A1 divided by omega D. And then X is minus zeta times omega n times T dot times A1 times cosine omega D times T. I'll copy that. Sine. And the settling time, tau is going to be 1 divided by zeta times omega n. And let's make t go to like 2 times the settling time. Or maybe just 1 time. Error? Did I make an error? Oh. Oh, you can put this guy? Are you talking about this little apostrophe? All this does is take the transpose of this. Like if you leave this off, linspace makes a row vector. If you put this apostrophe, it takes the transpose and it turns it into a column. And a lot of times I like to work with column vectors for different reasons. So that's the only reason I put that. So it's not an error, it's just kind of a matter of preference. Didn't know you can do that with lins. Yes, you can. Let's homework 5, problem 3. Guys, I messed up. Mine's going to 0. I messed up. A1. It's okay. Mine was a straight line, so you're doing better than me. Oh, shoot. What did I... Oh, I didn't put my particular solution. Plus D. Plus D. Let's run that again. Okay. That looks better. Okay, but notice it's only going... let's plot the 2 times the settling time so we can see its final value a little better. So it's going out to like 0.22 or something. If I want it to go to 1, actually we can use what we learned today. Let's say, look, it's like the output of this system is like 5 times too small, right? It's going to 0.2, but I want it to go to 1. So we have the principle of scaling. If I add 5 times the input, it's going to increase my output 5 times as well. So my input was just a scalar. I made it 1. Let's make it 5. Boom. Now it's a little bit too much, though. It went over 1. Actually, you know what I think it should be? Let's make it that number. Oh, buddy. Let's go to the settling time. Is that right? Let's compare to the original 7, 8. It's close. It's pretty close. What do you guys think? This is a challenging problem. I'll be lenient. I'm going to be lenient in the grading of this problem. But it's good. You were so close. Working backwards on problems like these, it's very, very good practice. Yeah, if you can do that problem, you're in very good shape with this stuff. I knew when I made that problem that it's very hard to do. So, do not be discouraged. Phil says, not in good shape. Well, just keep practicing. Continue to practice. I just wrote X in MATLAB, so I didn't want to rewrite everything on paper. That's okay. I understand the feeling. Oh, man. Man, the notes from today, they're a little cramped. Jeez. The whole digital learning thing is not my style. I like in-person office hours with real interaction. You're not the only one, Phil. I think we're missing out on a lot by not having in-person interaction. I agree with you. Ask Mr. Purge. I met with him practically every day. Yeah. I hear you. I hope they make an announcement soon about how the fall is going to look. Chris says, I personally like both for different reasons. It's, yeah. You know, like with Twitch, you can go back, rewatch stuff. You can just be chilling. I think this cuts out the same question being asked multiple times. Only benefit is the timing for schedules. Yeah, this definitely accommodates more people's schedules. Definitely rewatching this one. Yeah. Oh man. Hey Falcon, welcome. Phil says 2/3 done with the transmission. Finish the front differential and rear differential. Wow. That's impressive. How are you doing today, Falcon? All right, see you later, Phil. Have a good night. All is well, thanks. Good to hear. Chris says, is the motor looking good? I wonder how much the weight of the motor affects the system.
Morning, Shannon.
Okay, Chris, the only thing I wanted to check out on that is in the product specifications, it lists the stalling torque. And I'm wondering how powerful it is. Because, well, actually, you know what? We can get that motor, and then we might just need to lighten up the rest of the components. You know, like if it turns out it doesn't generate much torque, we just have to make all of the components lighter so that it can throw it around a little bit more. You've been trying to sell your drawing pad. Oh, nice. You know, oh, are you getting, you're gonna get a new one? Or do you already have a new one? Oh, man. Yeah, that'll affect how it recovers. If I'm wondering if it's worth looking at the original paper. Where did you go? Like, do they show how much? There you go. .23 Newton meters per amp. Like, that's what their motor was doing. I think the motor you showed me. Where is it? Stall current 2.5 amps. 2 kilograms centimeter. I don't know, it's probably fine. I think what this is saying, this 2 kilograms times centimeter, is that, oh no, is that if you take the motor and hang 2 kilograms off of it with a 1 centimeter moment arm, it has enough torque to hold that up. I would like to write an analysis paper on something of this nature after I understand it with more depth. Oh yeah, this is a great one to work through. Enjoy your evening too, Chris. Thanks for stopping in. As always. Hillary says, excuse me, I'd like to know your thoughts on nuclear deterrence as it relates to the Middle East. You see, I'm really a huge supporter of something I like to call flower power. Have you ever heard of that? I knew this would happen. What are you talking about? What do you mean? You see, flower power is a little thing where you spread love to your fellow man by just giving him a flower.
And I understand you have two misguided young brothers who need
Just a happy little plant. Makes him feel good inside. You know what I mean? What are you up to today, Hillary Bobillery? just woke up from a nap. Good. Now, was this the kind of nap where you wake up and you don't know where you are? You're reading about the history of nuclear power in North Korea and Iran. Whoo! That sounds like some light reading. You're fully oriented. Are you gonna have some post-nap coffee? That's one of my favorites. You're refreshed from the nap, and then the coffee just takes you to that next level. Drinking it now, baby! Wow. Good. Coffee saved my life this afternoon. Around 2 p.m. I was going down. I really like how you know how to read my words as I say them. I knew what you meant. Patty! You know what we should figure out soon, Hillary? We should do another Zoom game night or something. Jackbox is good, but I'm wondering if there's like other creative things out there that we can explore. I don't even know. Also, I send something to you and Hannah in the mail. It's supposed to get there today. Oh my gosh, it might have even arrived already. I haven't checked. There's one item in there that's for me that I'll really appreciate. I'm so stinking curious now. You're welcome in advance. Is it a piece of fried chicken? Well, I can't spoil the surprise, okay. All right, everybody. That's it for me. Hannah's cooking something delicious in the kitchen. I can smell it. It's making me hungry. Peace out. Talk to you soon.